So let's talk about me. So I'm a C++ developer at Jump Trading. I've been there since 2014, so getting close to 9 years. We're a trading firm that does all sorts of cool stuff, all asset classes, all time horizons. And yeah, so if you're kind of interested in that sort of thing, like feel free to talk to me. I've been a member of the C++ standards committee since 2016. I've been responsible for like a lot of work that's gone into it, especially in C++ 20 and C++ 23. Here's kind of smattering of some of the papers that I've worked on. Particularly relevant for today is I've worked on a lot of ranges papers, which kind of led me to the problem I'm going to talk about. And you can find me kind of on Twitter on Stack Overflow. I have a blog. I'm unreasonably active on Stack Overflow, so some of you may have run into my answers a bit. And kind of outside of the C++ world, I'm a pretty avid swim fan. So I also write for SwimSwam, which is the world's premier swimming media organization. And I used to be involved with this professional swim team called the DC Trident back when the International Swim League was still a thing, which was a lot of fun. All right, so let's kind of get started here. In the beginning, there was printf. So I'm sure everyone's kind of familiar with how printf works, but I'm going to go over it anyway. So the structure here is that printf takes a format string, which has some number of placeholders, and then a bunch of arguments later that are going to be substituted into those placeholders, where each placeholder is independent from every other. So if we run this, that gives us the price of beef is $12.34. So this %x tells us how to format the first argument in hex, and the %d tells us to format the second argument just as an integer. And so as we change the first placeholder, that's going to change the way the first argument is formatted, but it's not going to change the way that anything else works in that string. These are all completely independent, which is a pretty nice property. So printf overall has this fixed specification mini language. That is the grammar, in case you were curious. But printf is pretty limited as a facility. It's error prone because it's not typed. You have to provide the library with all the types of the arguments, and if you get them wrong, it's undefined behavior. But the bigger problem is that it's non-extensible. So if I have a type like point that I want to use, there's nothing that I can provide printf to print it. There's no way to extend printf for like all of our types. So it's a fairly limited library facility as a result. So then C++ introduced IOStreams, which has a very different look and feel than printf. Instead of having the format string as a distinct entity, we're just arbitrarily streaming things that we're alternating between a string-like thing or a non-string-like thing and whatever. So this in its entirety produces the price of $48.879 is $12.34, like whatever the cents are. IOStreams also has an ability to do manipulators, which are streamed in exactly the same way as any other arguments. So I just stream std hex, and that changes the way that the first int is formatted to look like the beef that I wanted it to look like, but it's also changing the way that the other int is formatted. These things are sticky. They have permanent effects. And so if we go ahead and add all the manipulators that the standard provides just up front, and these are all streamed the same way as any other argument, you can see that it's going to affect the next argument and also the one after that, but not quite in the same way. Right, so if you see that this one is 8 characters wide, which comes from the setw8 call, but this one's only 5 characters wide because it turns out while hex, show base, internal, uppercase, and fill are sticky, setw isn't, and that's just something that you have to know. So overall, we have in IOStreams, we have this fixed set of manipulators, which are mostly sticky, which makes them error prone. Because if you want to format an argument hex, you have to be very careful of undoing that hexness for everything else on your stream. But the big advantage to IOStreams, of course, is that it is extensible. So if I have my point class, it is very easy just for me to write a stream operator and make it printable. And this is just as printable as any other type in the system, which is fantastic. That alone makes it way better than printf. Now, I said that there's a fixed set of manipulators. That's technically not true. You can provide your own manipulators with IOStreams. So if you go on CPP reference, for instance, and you look up iOS base, which is the base class of OStream, you'll see down there somewhere this section called internal extensible array. And if you kind of like trawl through that and you read the documentation of those functions, you'll see that you can in fact write your own manipulators that are just as error prone as the standard library ones. All right, and then there was format. So the shape of format is very similar to the shape of printf. We have a format string with some number of replacement fields and then a bunch of arguments. And it works kind of the same way. Each replacement field is independent of every other, and each formats one argument. So as I change what's in the specifier, that's going to affect the way that that particular argument is formatted. It doesn't affect anything else. None of these things are stateful. Format also supports numbering arguments. This ends up being very useful for things like internationalization if you want to do translation of your string literals. And so one of the things that you can see with numbers is that, of course, you can flip the arguments around. You can format the same argument multiple times. There's a lot of things that you can do with this library. If we talk about the grammar, so I mentioned that these things are called replacement fields. Within a replacement field, if it has a colon, the part after the colon is called the format spec. It doesn't have to exist. There might not be a format spec. The format spec could be empty. The stuff before the colon is called the arg ID, which is also optional. There might not be an argument ID. In this case, both of the arg IDs refer to the first argument. They could refer to different arguments. There's a lot of flexibility here. The way you opt into formatting with format is through this type. You specialize struct formatter with your type, which has two template parameters, t and char. But for the purposes of this talk, I'm just going to pretend that the only character type is char because I'm not a Windows guy, so I don't care. So there's two functions here. One is parse. As you might expect from the name, its responsibility is to parse the format spec, if any, and to potentially save state that you need for the future. Notice that this function is not const. And then format, whose job is to emit whatever the representation is of this value, potentially using the state that you parsed, if any. And we'll go over both of these in some detail. So starting with parsing. The thing you get into parse is a specialization of this class, basic format parse context, which again, we're going to pretend just exists for char. And this is the complete API of that type. You can see that it has a begin and an end, which means it's basically a string view. Like these things are just string view const iterators. So you can't mutate through the format string. It's a read-only thing, but you do have this function to advance, which I'll get into a little bit later. And at the bottom here, we have these functions to manipulate arguments. So you get access to a given argument ID, either manually or automatically. And I'll also go into that a bit later. But before we even dive into parsing, I want to kind of stress that format strings can be arbitrarily complicated. So here's an example. This is a real thing that works. So you see in my format string, I start with asterisk, which is a fill character. Then the caret means that I'm center aligning. And then open brace, close brace is the width that I'm formatting this into, which in this case, because this brace is dynamic, which means it's provided as another format argument instead of being part of the string. So in this case, that is the 10 that is passed as another argument. So what this does is it takes my string, hi, and it formats it into a 10 character wide field, center aligned, padded with asterisks, which looks like this. So you can see that notably, there are braces in the middle of a format spec. That's totally fine. And really, and this could have used the manual numbering instead of automatic as well to refer to the arguments. Importantly, the spec can also contain arbitrary characters. So in the same way that the first example I showed, you can see braces, open brace and close brace as part of the format spec. In this example, which is called a chrono spec, I can format a time by just providing the way that I want my time point printed. And the spec has a colon in it that's totally fine. It's kind of whatever goes. And if you run that, that would print that date and time, which is the moment that I made the slide a while back. And which is nice, right? This gives a lot of flexibility. If you want to print your time point from chrono in whatever format you want, even if you want to print it month to year like a monster, you can do that. That's totally flexible. So let's go back to the first example and let's really kind of zoom in on this format string. So parse gives you this context, which is basically a string view with some different functions. What are the contents of that string view? Like, what does it actually refer to? And so that is actually unspecified, and it really kind of depends on the context that things are called in, which actual subset of the string you're going to see. So if we're dealing with the first argument here, you could see just that X. So starting from the first byte up to, but not including the close brace. You could see including the close brace, or you could even see up through the total end of the format string, including however many other replacement fields happen to be there. And similarly, in the empty case, you could see nothing, just an empty context, or just the close brace, or from the close brace all the way to the end. The most typical case is that you will actually see from the first byte of your format spec all the way through to the end of the string. And so you have to be very careful in the way that you manipulate these things. The simplest possible thing you can do for parse is just to return context.begin. So the contract here is that you have your format spec and you want to go through and see what's there, and maybe you reject some things because the user provided some format specifier that you don't support. And then you need to return an iterator that points to either context.end or the close brace that is the end of your replacement field, right? Because as I just showed, the format spec can contain arbitrary characters in it. It doesn't even need to be balanced braces. So you're the only one that really knows where the end is. So it's your job to inform the library where it is. So notably here, if we return context.begin, if our spec is empty, then we're returning context.end, so we satisfy the contract. If there aren't any characters in it, and so the first character is going to be the close brace, we're satisfying the contract by just returning an iterator to the close brace. If the user is providing another character, then we would be returning an iterator to that character, which is invalid, so the libraries can reject the format spec. So this works. If all you want to do is say that the only way my type is formatable is with open close brace, return context.begin. And don't return context.end, because that is consuming the whole rest of the string. And so if the string literal happens to end with a close brace, you're gonna break everyone else's formatting. Yeah.
So does it give you a pointer, a reference to the beginning after there was a colon? So like there was a 0 colon, you don't have to worry about
right. You're not worrying about the colon. It's always the first character after the colon if there is a colon, or the close brace if there isn't a colon, or possibly just like nothing, depending. Okay, so this example is kind of boring. Let's do something more interesting. So let's say I have my point type, and I want to support formatting it in either Cartesian or polar. And the way I'm going to do it is I'm just going to have a specifier that says, okay, well, if the user provides C for Cartesian or P for polar, to format it that way, or maybe also R for rectangular, because we want to be generous and to not have people remember what things are. So in order to do that, we need to store some state. We need to store this enum class to keep track of what our formatting type is, and we'll just have a default. Like by default, we'll format Cartesian. The user provides a specifier. We'll do what they say. So the first thing we're going to do in parse is if there's no spec. So if either context.begin is already context.end, or the begin iterator is already pointing to the close brace, so there's nothing there, we're done. We just return that iterator. If there is, we need to then read the next character and do something accordingly. So that is, we're just going to read the next character. If it's C or R, we're going to store our state as Cartesian. If it's P, we're going to store our state as polar. And if it's anything else, we're going to throw an exception because this isn't a specifier that we support. I don't know what the user is doing. This is wrong. And the nice thing about format is that this then will cause the whole call to not compile, which is pretty nice. And then at the end, we just return the iterator. So at this point, we've gone one character past, we've like consumed the first character. So if there was another character there in that specifier, then we're not returning an iterator to the close brace, so the library is going to reject it. So this is kind of all that we have to do. We just have to consume our one character. Okay, so now we parsed, we have our state. What do we actually, how do we use it? In the same way that there's a parse context, there's also a format context, which looks like this. But I'm going to drop char, so it really looks like this. And I'm also going to drop locale, so because I don't want to deal with it. So really, this is the format context API. I know this one is pretty interesting. It's quite different from the parse context because we still have this template on the output iterator. Now, we don't know anything about this output iterator type. It can be any arbitrary type that satisfies output iterator of char constref. And output iterators are kind of funny things. So we'll kind of get into the consequences of that. Not all of our output iterators are going to be as nice as just char pointer, for instance. So what we have is we have our ability, we have out, which gives us the output iterator. We have advanced to, which informs the context that we've written something into this output iterator and to adjust its own internal state, which we'll see in a minute. And we have this arg function to get access to other arguments other than the one that we're currently formatting. So basic format args here is basically a variant of a bunch of types, and we'll see that in more detail later also. But the important thing to keep in mind is this variant is templated on the context, which is also templated on the iterator. So that'll play an important role later. So the simplest example I could think of was, let's say I have a type char that just has a member char, and it doesn't support any format specifier, so its parse just returns context.begin. And all formatting does is I'm just going to write this one character into the output. So I need to grab context.out, I write my one character into it directly, and then I just return the iterator. So that's what the contract of format is. You write whatever you want. And so while you could resort to like very low level writing single character at a time through the output iterator, typically you're going to want to use higher level functions for this, which are available. So if going back to formatting point, one of the APIs is format2. So format2 takes an output iterator and then a format string and a bunch of args. So this ends up being pretty nice. I'm implementing format basically in terms of format just for lower level types. So if I wanted to implement Cartesian formatting, I could do format2 context.out, and I write my format string, which is just parens x equals whatever, y equals whatever, with p.x and p.y. Except that what I really wanted to is format either Cartesian or polar, which is just like an if statement, and then I pick one or the other formatting. And that's it. And with that, if I print, Lagrange point is IP for my type, that'll print by default like this, because that's what the default formatting is for point. It prints rectangular. But if I provide the p specifier for polar, that'll print this representation instead, because the default formatting for double happens to be the shortest round trip accurate representation. I don't remember the exact wording because I'm also not a floating point guy. But if you wanted to reduce the number of decimal points there, that's available to you to just change the way you want to format it. So let's talk about dynamic formatting. So with this example, okay, so like I can format my point in rectangular, I can format my point in polar, but I need to commit to that choice at the point of the string literal. What if I can't make that commitment? Like, what if this choice is coming from like some user-defined input? Like, I don't have that at compile time. And so what I want to do is I want to provide that argument later. So as a kind of dynamic argument input into my format spec, in the same way that you can pass in a dynamic width, like the example I showed earlier, or maybe like number it manually. And then so if I change it to pass an R, it'll format this way. How do you make that work? So that's a little bit more involved. So we start with, we need to add more state. So now we have this third kind of coordinate type, which is dynamic. And we need to also keep track of the argument ID. I think maybe if we had a language variant, this would look very different. You would just have a variant of Cartesian and polar being empty types and dynamic being a type with a member size t. But because variant is a little awkward to deal with, it's just easier to make them separate members. So if we go back to our point example, it becomes a little bit easier to swap out the way the switch works. So now we have another case to consider. It's not just C, R, or P. We also have this case. It's like, okay, well, if the next character is an open brace, now what do we do? All right, so if it is an open brace, then we know we're dynamic. And now we need to parse the rest of what's going on in the specifier. So if the next character is a closed brace, which was in the first example I showed, now this is manual indexing. So I need to ask the context for what the next argument ID is. I'm going to stash that. And then I'm done with that case, because that case is just open brace, closed brace, there's no other characters. Otherwise, this is the manual numbering case. And so now I'm expecting there to be a number there. So I need to parse out that number, which I can use from chars for. It's a little bit awkward in this case because from chars takes specifically char const star, and what we have are string view iterators, which are implementation defined, which are allowed to be char const star, but aren't necessarily. So this is just doing from chars. And then, so if the parse succeeded, so the error will actually be error C, and the parse stopped at a closed brace, right? So this is the case. So the parse is going to fail if there's like integer overflow or something like that. And from chars will stop when it gets to a non-integral character. So we need the non-integer character that it stops at to be the closed brace, because we need to be consuming the whole thing. So that's just checking to make sure that the iterator that we end up at is not end because it needs to be a closed brace and that the character is a closed brace. In that case, okay, finally we have an argument ID. Now we need to call check arg ID to validate that this number that they passed in was actually like legit, right? The user didn't pass in 42, but there was only 3 format arguments, so there's just no 42. So this API right here this is like your automatic and manual indexing API. All these do is check to make sure that these are valid arguments. And in both cases, we end up with some arg ID that we're going to use later. All we have at this point, like we don't have any way of getting the value of whatever that argument is. Like we don't have a way of accessing the value of the char. We just know that like, okay, it's going to be index 2 or index 5 or whatever it is. And that index is real. There actually is an argument at that index. So once we parse that out, now we need to update our format to actually use this information. So what does format need to do? So we're no longer just Cartesian or polar. Now we're Cartesian, polar, or dynamic. And where dynamic is either Cartesian or polar, we're not sure yet. So the first thing we're going to do is produce this local version of the type. And then if the local type ends up being Cartesian or polar, then we're done. We already know how to format those things. So if the type wasn't dynamic to begin with, then our type is just whatever our type was. Like that, it's already Cartesian or polar, so that's all we need. If the type was dynamic, then we need to go back to this arg API. So arg gives us a variant, and then we need to visit that variant. And that variant has a lot of different possible types that it could be, but we only support char. So if the type happens to be char, then we go ahead and now we have access to this char right here, and we need to do the parsing and check to see if the char is CR or P, the same way we did before. I'm not repeating that code. Otherwise, if the type isn't char, then we're going to throw an exception because we're expecting, the character P. We're not expecting the number, 85 or something, or a string or whatever. So this is our API. So we saw the parse side API to give us access to the argument index, and this is now the format side API to give us access to the argument value. Does that make sense so far? All right, yeah. Yeah, so what check arg ID does is we have a number, and we don't know if that number is valid. So check arg ID is basically just a bounds check that the number is actually like there is an argument at that index. So if I pass like 2 formatting args and I'm parsing number 1, then check arg ID 1 is going to be fine because there is an argument at that index. But if the user provided like 6, well, there isn't. So that would throw an exception at that point. Yeah, so if you call like std format directly, that would be a compile error. If you call one of the other APIs like vformat, then that'll end up being a runtime error. It depends on the context. Yeah. Cool. So let's talk about generic formatting. So we saw how to format points where we knew what all the members were. They were just ints. So let's talk about formatting optional. So if I want to format optional T, so we can start by saying, okay, again, I'm not going to support any format specifier. So parse just returns context.begin. And because Rust is cool, what format's going to do is if I have a value, I'm going to format some with the argument. Otherwise, I'm going to format none. This formatting makes sense in Rust. It makes no sense in C++, but we gotta print something. So this is already pretty useful. We got some output, but it would be nice to get really the full richness of what we can do with the types, right? It's like I can format my int as hex. So maybe I want to format my optional int as hex if it has a value. Like maybe I want to pad the underlying string. Maybe I have an optional point that I want to format polar, right? So how do I do that? So the only access I have to formatting a T is using formatter T. That's the API. So I start by having a member formatter T. Parse, I'm just going to completely defer to that underlying formatter. So now whatever specs T supports are the specs that optional T supports, and whatever goes there. So now I have that state. So now I just need to use it, right? Because right now I'm not using that state. I'm just formatting my optional using open brace, close brace. So that's not like useful. Like I consumed the state and I completely threw it away. So step 1 is I'm just going to split this into 3 pieces. So I'm going to do the string part of sum and then format the value and then the close brace. So our only way to format using formatter is the member format call. So this needs to look like this somehow. So what's the context that I pass in? Well, I have my context here. But the thing I have to remember to do is I have to do this two-step of context.advance to out, and then call format. Because the first line, I wrote something into the output iterator, but the context doesn't know that I wrote those bytes in through that output iterator. So if the output iterator is something that has state, so char star, the context needs to know about it, so that when I format the underlying type, I'm not just overwriting the bytes I just wrote. So this is going to be like a really tricky thing to get right, because if the output iterator is something like back inserter vector of char, where every back inserter to the same vector of char does the same thing, like they're all just going to push back on the vector, you don't need to do the context out advance to out. It doesn't like change the state of anything. These things are singular anyway, and so you won't see that as a mistake. But there are certain APIs that you can construct that you can get to stuff like char star as the iterator, in which case, if you don't update the context state, you're just going to overwrite your own bytes. So that's a bit tricky. But otherwise, this is an approach, right? So parse is implemented in terms of underlying.parse. Format is implemented in terms of underlying.format. And now all the specs that T supports, we support for optional T, which is pretty nice. And it's not like that complicated, right? Outside of that one kind of gotcha. All right, so formatting ranges. Slide 78. We finally get to the title. So what makes formatting ranges interesting? So one of the problems is that there's a lot of different formats that people might want to use for ranges. You know, the simplest might be, okay, well, I just have my sequence. It's limited by comma space, and they're surrounded by square brackets, which nests pretty naturally and is pretty easy to read. But if I'm formatting strings, it might be useful to quote the strings. This is something pretty typical that a lot of languages do, especially if your strings contain things like commas or spaces in them. It's a lot easier to tell what elements you actually have if you quote them, or if you have characters, if you escape the characters, does help a lot. But maybe you don't want the brackets in the particular output you want. Maybe you want to do some kind of alignment or padding of your type. That's also pretty useful. Maybe your range is a dictionary, and you want to have a formatting that is more associative and kind of expresses that relationship between your types better. So, or maybe you have a set. So square brackets isn't quite what you want. It'd be better to have braces. So even if we just focus on vector of char, right? You know, I think this is a pretty good default for how you might want to format vector of char. But maybe you don't want the quoting or the escaping. Maybe you have chars, but they're really like ints or in hex or hex with a base, or like this is a MAC address, so you wanted to limit it with colons, or like it's a vector of char, but it's really a string, so you want to print it as a string, quoted or unquoted. So the point here is that there isn't really like the way to format vector of char. There's a lot, and while I think the first one is a pretty good default, if that was the only one that we supported, lots of people would be unhappy. And so we have this space where we have this library that supports all these specifiers. So how do we use them here? Like how do we take advantage of that? So one of the issues here is if we look at like what a format spec for an arbitrary range might be, is we don't know where this close brace is. We don't know anything about the underlying type specifier. We don't know how to find the end. The only thing that knows how to find the end of a type specifier is the type's formatter. It's so like if we can't just look for the next close brace, because the next close brace might not be the actual end of the format spec. There could be arbitrary other close braces into there. This example is nice because it's balanced, but like there's nothing stopping someone from having arbitrary many close braces in their format spec because I don't know, they just don't like, they're antisocial. So we have to rely on the underlying type to know how to parse itself. We can't really make any assumptions there. So the key there is that whatever the underlying format spec is, it kind of has to go at the end, because like it can get us to the end, but the only thing that it can find for us is that close brace. So any kind of like top level specifiers that we want to provide, things that affect the range itself, but not the underlying elements of the range, have to go in front of that somehow, right? And of course, like after a colon, because there's always a colon. So for instance, if the underlying specifier that I want to use was X, that would have to go there. And if I wanted to support hash X or D or n-3, which is center aligned 3 characters using n as the fill, which is fine as any fill character goes. But then I might want to support a top level specifier n to say no brackets, n for no brackets. So now I don't have my square brackets. So the problem is, like, how do you differentiate between the n for no brackets and the n that's the fill character for the underlying type, remembering that any character other than closed brace is a totally reasonable fill character. And the key there is, like, well, we can just use colon. We can say that the top level specifiers are everything before the the next colon. And then if there is another colon, then the stuff after that can be the underlying type specifier. And the nice thing about this is that that approach nests very well. So if I have a vector of char, I can say that that part of it is the specifier for the whole vector of char. This part is the specifier for vector of char, each one of them. And then this is just the specifier for each char within each vector of vectors, right? So here's printing that using hex with the base. And then if I want to pad each one with asterisk, and then I want to remove the top level, but not the inner level brackets, this nests pretty nicely. Okay, so how do we implement that? So the first thing to start with is, okay, so which type do we use for our underlying formatter? So the key here is that ranges have a value type, and we're not going to use that. Instead, we're going to take the reference type and we're going to remove cvref on it. For most ranges, that is the value type. For most of the common ranges that you'll encounter, because the reference type will either be something like, intref, inconstref, or int, and then the value type will just be int. So those are the same type. But in cases where you have stuff like proxy references, the reference type might be vector of bool reference or tuple of intref, in which case the value type there is something else. The value type is bool or tuple of int. And if we wanted a formatter of the value type, we would have to construct value types. But there's no reason for us to pay that cost anywhere. So we want to stick with reference everywhere. This is like another thing to keep in mind for ranges, is that unless you specifically need to construct values, you want to use reference type, the reference type. So for now, parse, we're just going to defer. We're just going to call underlying.parse. I'm going to skip the top level specifiers for now. So what does format do? Format takes my range and it takes the context. So we're going to surround ourselves with square brackets, and we're going to loop over the range. We're going to print every element. And that's our 2-step. We're going to advance the context to our new output iterator, and then we're going to use underlying.format to format our element. And then last but not least, we have to add the comma after other elements, except for the first. This isn't the optimal way of doing this, but it doesn't super matter for these purposes. Okay, so given that, that's not so bad, and that's already pretty good, right? So that we can format a vector of int, and that works just fine. We can format a vector of ints, that works just fine and prints the thing we want. We can format things with hex, which is cool. We can use specifiers, and that also does what we want. We can use range adapters, like if I use views transform, and this is using boost lambda 2 for just to double every element. Also fine, totally works. This is cool. And then I try to use it with filter, and I find that it doesn't compile. Well, that's annoying. So what happened here? So the issue is we took our range by reference to const, and so we're looping over a const reference here. But filter is not const iterable. There's a bunch of range adapters that the mutable version is a range, but the const version is not a range. And there's a wide variety of reasons that ranges might not be const iterable. Filter needs to cache begin, but other ranges actually need to mutate their own state. That's kind of inherent to the way that range works. So this doesn't work because, well, our const filter isn't a range so this doesn't compile. Like the loop, just we can't do it. So the initial solution might be, okay, well, we can use views all here. So views all that just takes a range and turns it into a view, which doesn't really do very much. So for the filter case, it's just going to copy it for us, and that copy is not const. So we can iterate over it because it's mutable. So that works for that case, but it's expensive because we're copying this thing for seemingly no reason. And there are other cases that are move only. So you can have move only ranges that you just can't, or move only views that you can't copy like this. That still doesn't work. So we're kind of limited here in our scope of things that we could do. And ultimately, the problem is that if you look at what the API format looks like, every single entry point into format takes a pack of references to const. And so once you have something that's const, it's const. Like there's no going back. Like and no, the solution here is not just like const. It's RF. We're not playing that game. So this is why Viktor Zverevich wrote this paper a while back now, because there are types that are move only non-copyable views, like std generator that we just added in C++ 23 that people are going to use. They're going to want to have them work with this facility. So that what that paper did is it changed all of these APIs to take a pack of forwarding references instead. So what that means is, okay, well, like now if someone passes me a mutable thing, that mutable thing will eventually be passed down to my format. So I can take it as mutable if I want to. So I can go back to my format and I can change this now to just RF for rconstref. Of course, now this has the opposite problem is that like, okay, well, now I can print all the mutable things, but if someone actually gave me like a const vector, like it's not gonna work. So that sucks. So the next step might be like, okay, well, I'm just gonna write two functions, right? I'm gonna write a format that takes an RF, and I'm gonna write a format that takes an rconstref, and have them both forward to this function template that takes either. So this works. This is a viable solution. But then if you think about like, what is the point of this overload right here? So if rconst is actually a range, that's the one I want to use. Like that's good enough. Like I can just use it. Even if you give me something mutable, like I don't need to stamp out two different versions of formatting this type. The const one is fine. But if the const one doesn't work, then this is the only one I need to have. Like I need this one. The other one isn't viable. So the real thing is like, well, let's not provide both. Provide just the one that you need, which is what we're doing. We have this thing called format maybe const, which is just okay. If this type is formatable as a const range, then use const. Otherwise, use R. So basically, this part is no longer a template. There's only one format instantiation per type per context. It's just the one that we need. And so now that we can actually accept our filter as mutable, the filter case works. Cool. And prints 20 and 30, which are the numbers above 15. So cool, making progress. So let's talk about specifiers now. Because I skipped them in the beginning, I started to come back to them. So the simplest one is just the no bracket specifier. So if the user provides n, we're not going to print the square brackets. We're just going to print all the elements. And so I'm not going to bother with parse. That's it's not very complicated to parse out the n. And all we have to do is the places where we printed that square bracket, we just only conditionally printed instead of unconditionally. No problem. Let's go on to fill align and width. Right. This is a pretty useful aspect of formatting. I personally use it like all the time because you want to line stuff up. It's very nice. Unlike the no bracket specifier, fill, align, and width are quite challenging to parse. So I'm going to skip that for a different reason, is because I just don't want to show that code. But let's pretend we have it parsed. Right? We have this object format specs, and it has all the information that we need of the fill, align, and width. Okay, so how do we use it? All right, so let's say we had a string like hello, and we find out that we need to parse the string into a field that is 7 bytes wide, right aligned using hyphen as the fill character. So there's two kind of general strategies for how do you format this thing in the right way. So you can count how many characters you have, in this case 5. And so you can subtract that out and be like, okay, well, I need to format 7 characters. So I'm going to format 2 hyphens and then write my string directly. Right. So that's one strategy. Another strategy might be I'm going to write my string and then I'm going to insert hyphens at the front until I achieve my goal. Okay. So which one of these strategies should we pursue for formatting ranges? So one problem is that context.out is an arbitrary output iterator, right? We don't know anything about it. And it might be a write once iterator. It could be a back inserter into a vector or a back inserter into a string. It could be something even more write once. It could be like send this char over the network somewhere. So this whole strategy of like, I'm going to write something and I'm going to change my mind and I'm going to write something else, that's not going to work. The second thing is I have no idea how many characters to write. In the string case, like, okay, string.size is how many characters I have to write, but I have a range. It might not be a sized range. I don't know how long it is. Importantly, like it might be an input range, so I might not even be able to iterate this thing twice, right? And even if it's not an input range, so I could iterate this thing twice, I might not want to iterate this thing twice because iterating it might be expensive. There might be a lot of calculation involved in advance of the iterators. Like I don't want to do that. And then we have to format it into this context, right? This is the context that we have. Okay, so how do I do this? Right? These seem like mutually conflicting criteria that don't let us do anything. Okay, so let's kind of figure something out. We don't necessarily need to format into that context. We need to format into some context. So what if we could construct a context that we know things about that we could then use to make this problem more amenable to a solution? Okay, so let's kind of start out and vector of char. Vector of char is a nice type. We know a lot of stuff about vector of char. So what if I format into that? Like, what if I construct a new context that's going to use back inserter of vector of char as my thing? And instead of writing into the original context, I'm going to write into this new context instead. That's fine. That still only involves iterating over this range one time. And then at the end, I'll have all my characters into my vector of char. And once I have that, well, that's easy to deal with, right? Now I know how long it is. I know how many characters they are. I can just implement this write padded line function. That's no longer complicated. This now becomes the only use of context in this entire function, and I'm writing buff into it, and buff is just a vector. So this is now becoming like an exercise in like, can I do math properly? Cool. So how do we go about doing this? And so this is really the key. So okay, how do we construct our own format context with our own iterator? So go and look at the spec, and the spec is kind of sparse for format context. In particular, you might notice that there's no constructor there. So that kind of limits our options, but that's okay. Let's pretend that we can go ahead and we'll add a constructor that takes an arbitrary output iterator and just make it do the right thing. But now we have this other problem. So underlying.format can do lots of different things. In particular, it can use this arg API to get access to the other format arguments in case it needs to use them to determine things like dynamic width or like dynamic point type or whatever. And so like the arguments had better be there for the user to access. Otherwise, we're kind of like pretending that it works and then like suddenly it doesn't work. Okay, so I need to pass the arguments into this context that I'm constructing. And now we run into this other problem, which is that args is templated on the context, which is templated on the output iterator. So that happens to work if the output iterator I happen to pick is the same one as the original context, which of course there's no guarantee in general. And given an arbitrary output iterator, there's no way for me to necessarily provide a nice different target for it. Okay, so I'm kind of stuck. So let's talk about basic format args a bit. So basic format args is, roughly speaking, a span of basic format args context const. So it's not mutable, but these things are contiguous. So what's basic format arg? It looks like this. It has this variant with a whole bunch of types. So these are all the common types that people are going to be formatting all the time. So it's more convenient and more efficient for them to get like first-class treatment. So you have bool char, you have like all the integer types, you have all the floating point types, char const star, string view, void const star. And at the end, it has this handle type. And this handle, which is implicitly templated on the context, but we can kind of switch this around a bit and pretend that it's explicitly templated on the context. And this handle is what format uses to format all user-defined types. Basically, any type that isn't one of those is going to go through handle. And what handle basically looks like is this. It has some void pointer for the data, and it type erases a function that does both formatting and printing in one go. And importantly, like this type erasure is inherently based on the context. So if I'm formatting a given type, the library is going to type erase how to format that type for the context using the output iterators that it's actually going to use to eventually format it. So what we want ultimately here is to take this variant from our original context, and we need to convert it to a variant of the other context in order to be able to construct our new context with this new output iterator. Well, it might be a new output iterator. We have no idea if the types are different or not. And so if we kind of start like looking down the types, well, like, okay, well, converting monostate is easy. It's just like, okay, well, it's like monostate. And converting bool is easy. And we can kind of go down the list. Like all these types are just the same. So like converting most of this variant is trivial because we just preserve it. The only one that doesn't work is this handle conversion. And this is like actually impossible. We can't convert a handle for one context to a handle for a different context because we have no information to do so. We type erase one function pointer. We can't produce another function pointer out of that. We're not going to be like, let's just proactively type erase lots of different contexts just in case. That's like horribly wasteful, and you can't type erase every context anyway. So it isn't going to work. But the key insight that we can make here is that these types are actually useful. If you're writing format and you're actually getting access to an arg to use as part of formatting your type, like it is useful to try to get access to a bool because you get its value. It's useful to get access to an int because you get the value of the int. It's useful to get access to a float, to a string, whatever. It's not useful to get the handle, like, because you can't do anything with it. The only thing you can do with a handle is that format function. But that format function doesn't just do formatting, it does parsing, and you don't have a way to produce the parse context to give it anyway. So like this type is just useless. So what we can do is like, what if we just don't preserve that one? Like what if the original arg was a handle, we just give you back monostate? Well, I mean, you weren't going to use it anyway. So we're just changing it from one type that you have no use for to a different type that you have no use for. It is technically a loss of information, but like, are you really going to notice anyway? Probably not. So maybe that's fine. So let's say we introduce this new API called retargeted format context. And what this is going to do is it's going to do that argument conversion for us and then produce like a new context for us using those new arguments that we can actually use. And importantly, like it might not need to do the argument conversion because we could have actually picked the correct output iterator. If we pick the correct output iterator, then this is free. And for instance, using the format library, the correct output iterator type in almost all cases happens to be format appender of memory bus. So if I know that and I'm just like writing my implementation, I can just use that and have this as a cheap conversion, for instance. It's not always the output iterator type. And there are situations when this is still like a conversion that has to be done. But at least it's pretty cheap for most cases. And so this works now, and you can see an implementation of it on Compile Explorer. I have the slides up somewhere, so you can click through these links, and this does work. So once we can actually construct the context that we have, this alignment is easy. Like we get something that we can then manipulate as we want because we just have like nice data. We don't have to deal with, I have an arbitrary range with arbitrary category of an arbitrary type. Okay, so let's talk about delimiter, which is the next kind of interesting top level specifier. So I have a MAC address that I want to format, which is a vector for some reason. So by default, uint8 in format prints as integers, which is what you want uint8 to print as. In iostreams, it prints as a char, which is has been for me a very common source of bug when you try to print some like network representation that uses uint8 that has like 2 in it and it ends up being unprintable. So that's one problem the format solved for us. Okay, so I want to print it in hex, and I don't want the brackets, and so I'm almost there. All I need to do is change the delimiter from comma space to colon. And so what format has for this is it has something called join. So join just takes a range and a string view to use as a delimiter. And you can see that the specifier now is a little bit different. There's one less colon in it. There's only one colon instead of 2. And this works. Here's my MAC address. I'm happy, but I'm not like super happy. I'm kind of like very ambivalent about this API. And the reason I'm ambivalent about this is if we look at different contexts in which we might want to format a MAC address. So if I have one MAC address that looks like this, if I have a range of MAC addresses that I want to format, I need to do this, right? I need to have my range of MACs. I need to pipe it to views transform, and each to transform each element using join to get there. And then if I want to add padding and alignment, I guess my favorite example in this talk, that's not supported natively by the join view. So what I need to do is I need to first use format to get my string, and then use the specifier on the string. So these all work. These all like get the job done. But these look very different, like these three things, even though I'm fundamentally trying to do the same thing. So if we had a top level specifier for delimiter, let's say we introduced it with the letter D, and then maybe like and then an arguments placeholder. So in this case, open brace, close brace to give me the next argument, and I pass in my colon to get there, right? So this is the way that I'm specifying the thing. Or maybe I even go one step further and allow you to embed the specifier into the format string, because in the common case, when you want to provide a delimiter that isn't comma, you know at the point of writing it what it is. So it'd be nice to just embed it. Delimiter is, of course, pretty complicated because it can be multiple characters, and then you have to figure out in the specifier, well, like, how do I bound it? And there's only so many different brackets. Although when I was working on this, I discovered that like there's a lot of different brackets in Unicode, but we probably don't want to go all out. But the nice thing about this, and the reason that I kind of like this approach, even though it does make the specifier more complicated, of course, like we have colons that have very different meanings in the specifiers, is that it's all in the same order, right? Like the specifier that is like, how do I format each character of my MAC address is always at the end. The specifier for how do I format my range is always in front of that. And these always look the same. Versus in the other example, they're all in different orders. And it just like really depends on what you're doing, what it looks like. And you can see an implementation of this, like the difficulty in having a delimiter specifier, unlike fill parse align, the delimiter isn't like, how do I format this thing? Or even how do I parse this thing? It's, is this a good idea at all? Like, do we want to make format specifiers more complicated? And I think it's kind of worth it. Because it's, I don't know, I kind of think the thing on the right is a little bit of a mess, and the thing on the left is cleaner despite the added complexity of the specifier. But this is a choose your own adventure kind of thing. So let's get into formatting tuples, which is really the final boss of this whole problem. So let's say we're formatting a pair of ints now. So what does the spec for this look like? So we know we have to start with a colon, and we know kind of from our experience with ranges that the rest of the structure has to look something like this. We have the top level specifiers for tuple, and then we have the specifiers for first and second, right? And so like ideally we want to support something like this where we can provide one kind of specifier for first and a different specifier for second, and like we don't have any top level specifiers for tuple. And like, that format's like this, because that is what those specifiers mean for int. But the problem is like, okay, how do you find this boundary? Because with ranges, we were at the end. We were always at the end, and we just leave it up to the underlying type to find us the close brace. But here we're not at the end. We're still in the middle. There's other stuff after us. How do we tell things where to stop? And reminding that like, because these specifiers could be arbitrarily complicated and have colons or braces in them. How do we know where the end is? So one approach is, well, these things know how to find closed braces, so let's give them closed braces to find. And so we wrap every specifier of every underlying element of the pair tuple in an extra set of braces. All right, so if we look at this from a high level perspective, and we start parsing this thing, we're going to pass this blob into first formatter's parse, and that blob is the only thing that like it knows that it's not this closed brace, but this closed brace that it needs to find. So it's going to return that closed brace to us. And then we can skip the next open brace, and then we're going to pass this to second formatter's parse, and that's going to find this closed brace for us, and then we're done. And so we can use that to basically determine that these are the two specifiers for the two types, and they're both nicely bounded with braces. And of course, like these can be empty; they don't have to be populated. But even in the empty case, we need braces there. Okay, so how do you implement this? This isn't so bad. So if I'm formatting tuple of t's, I have a tuple of formatters of the underlying types. Again, remove cbreft. So what parse does is, so we start with our same check as usual. If we don't have anything to do because begin is already at the end or points to a close brace, we're done. Otherwise, tuple for each. So if this function isn't in your toolkit, I suggest adding it because it's pretty useful. All it does is stamp out this function for every element in the tuple. So in this case, we're iterating over our tuple of formatters. So F here is each formatter in turn. And so what we're going to do is for each one. So first, we're expecting an open brace. So if we're already at the end or we're not in an open brace, that's an error. So we throw an exception. Then here we have to advance the context. So this is the first time that we're using the parse context advance because we need the underlying type to start at where like we want it to start at and not the very beginning of the tuples format specifier. And then we're going to call its parse to tell us where the new end is. And that new end needs to be a close brace, right? It can't have hit the end already. It has to have, there needs to always be a close brace. If we don't hit a close brace, that's an exception. Otherwise, we just move on to the next character and we're done. That's actually it. This is our full tuple parsing, which is, I mean, I think that's pretty nice. On the format side, it looks pretty similar, except instead of tuple for each, we need to do a tuple enumerates. This could also potentially be a tuple zip because now we need to, because we're iterating over both our tuple of formatters to get our state and the tuple of values that we're actually formatting. So tuple enumerate gives us this index. So the key here is mainly that we're just calling context.advance to out and then f.format on std_getAbi of the tuple, and then dealing with open paren, close paren, and comma between every element. So that's not so bad, and you can check out the implementation here. You know, it sounds so terrible. So, but it kind of has this weird aspect, which is if you look at the spec that I showed, and there's two places in this format specifier that we just have open brace, close brace. The first one of these was a dynamic width as part of the chrono time point that we're formatting. And typically when you see like a nested open brace, close brace in another replacement field, that's going to be like a dynamic argument. That's like dynamic width, dynamic, you know, whatever. But this open brace, close brace is a format spec for the second element of the tuple, or whatever. So now we have like format specifiers are already kind of complicated. And as they become longer, they're going to be more complicated and they become more difficult to read. So like having the same character sequence mean different things in very close proximity of each other is confusing. Like it's hard to read. It's hard to understand. We're getting dangerously close to Perl here. So is there something else we can do that like maybe doesn't overload the meaning of this expression? So we kind of have to go back to the drawing board. So we need some way to find these barriers between these pieces. And there's no like magic character that we can choose in advance that is that barrier because, well, the chrono specs can use any character. You can use almost any character for the fill character if you're formatting like a string or int or something. So we can't like a priori say like colon, because that's not going to work, or hyphen, because that's also not going to work here. But kind of the key insight that Tim Song came up with is that we're not the only people that have ever had this particular problem. Like, how do I pick a delimiter for an arbitrary string that can contain arbitrary characters in it? So what does sed do, right? So sed is like, well, you choose a delimiter for me. So you can say like, okay, well, what if the user picks a character and it's kind of up to them to pick something that's unique. So that could be a pipe, maybe that's comma, which works in this case. Maybe that's capital Y, which also works in this case, although probably not recommended. And as long as the user picks something valid, that's fine. Like, we don't care. And that's kind of an interesting approach. But how do you actually make this work? Because people have already written their formatters for parse, and parse is not looking for capital Y. It's looking for a close brace or end. Now we can't change this to like look for a different character, and we can't change the format string to suddenly have close braces in it, because these things aren't mutable. So our only other option is like, well, what if we change where end is for the purposes of calling parse? So let's see what we can do. So we'll start over here. So the first thing now we have to do is we pull out the first character. That's our delimiter. This has to be a single character. And then we're going to go ahead and skip it, and we're back to doing our tuple for each. So now the first thing we're going to do is we're going to look for that next delimiter. So before we couldn't do this because like we can't just look for a closed brace, but here we can because the user is promising us that this is our legit delimiter. And if we don't find it, it's a bad format specifier. Now the thing that we have to do is we have to call f.parse, but f.parse needs to stop at this delimiter. And the only way for f.parse to stop at this delimiter is if we change context.n to actually refer to that delimiter. So what we can do is we can stash away what the real end is, temporarily set the end of that context to be the delimiter. And then when we're done parsing, like restore the real context.n so that in the next iteration, we can keep looking ahead. And also like if there are other format arguments that like they actually work properly. So this part right here is like just screaming to be a scope guard. Like this is something that we're like temporary mutation that we need to do that we better restore at the end. So we can call this, for instance, let's say end century. So what end century does is it's going to temporarily swap out what context.n refers to be this character, and at the end restore it to the original. And you can see an implementation of that here. Now this also requires further library changes because there's, if you recall, there is a context.advance2, but there is no context.setEnd. So you might wonder how I implemented this, but remember that this is C++, where private doesn't really mean private. All right. So what that means is that these are kind of our choices, right? We can either go with the first approach where we just surround every specifier with an extra set of braces, or we can go with the second approach, which is just like let the user pick a character. So this is what it might look like in the empty case where we have this issue where open brace, closed brace means different things in different contexts, or like this is what it looks like if we had a single character. Now, the brace version nests a lot nicer because you can imagine if we're printing like a tuple of tuples, you can follow the closed braces, and most IDEs will like highlight where the next closed brace is, even if it's within a string literal. This like nested keep picking distinct characters gets tiring fairly quickly, as you might imagine, especially because it's like basically impossible to actually find where the next one is. So okay, so look into C++ 23. What do you all have to look forward to as we're finalizing the next revision of the standard? So 2 years ago now, I read R0 of this paper, which is pretty short. It was only 8 pages long. Amusingly to me, it included this sentence, which reads, "The choice of formatting is implementation defined." Which is, at the time, I was like, well, I don't really care how these things are formatted. Like literally any formatting is better than no formatting, which is the status quo. That turns out to not have been a popular choice, as you might imagine. So the last version of the paper is 42 pages long, but it was adopted for C++ 23. It's in there. And so what's in there? So we have formatting for ranges and tuples. It has a lot more stuff than actually what I talked about in here. There's a lot more different kinds of specifiers. That has a convenient utility for doing range formatting. So if you have your own custom range type that you don't want to use the default formatting for, and you want to implement your own thing, you can use range formatter to make it a lot easier to implement whatever you want to do. You don't have to implement like all of that kind of from scratch. It has a bunch of specifiers. So for instance, if you have a vector of pairs, that what it really logically represents is like a map. There's a specifier M to print it like a map, for instance, because not all vectors of pairs are maps, but some are. And so tuple has a bunch of specifiers for fill, line, and width, and also map. Now there's no delimiter specifier here, for instance, and this also supports string and character escaping. There's also, separate from this paper, but in a different paper that was also adopted, there's a way to make it very easy to opt into. So like, let's say you have your own custom hash table. Your hash table, you want to format it like a hash table. And in order to do so, you don't have to actually implement all of the formatting machinery to do so. There's just a variable template that you can specialize and say that this type is a map, and then it'll format as a map by default, which I think is pretty nice. And on top of that, if your custom hash table looks like standard library hash tables, that'll come out actually by default. I don't actually remember what the exact heuristic was that we used, but we picked a heuristic that we felt was sufficiently unlikely to have any false positives, but fairly typical, like a lot of user-defined hash tables. So like all the boost ones, all the AppCell ones, we'll print as maps without any code opt-in. So work that isn't in 23 that we still need to work on. So while ranges and tuples do support the fill pad align kind of thing, you won't be able to write that for your own types because we never settled on this retargeted format context thing. So that's not something that you can implement without library help. There's no delimiter specifier for ranges, and similarly, there's no format join equivalent. One of the other problems with format join is like, well, once we add it to the standard library, like what do we actually call the thing? So there's also no element specifier for tuples. If we go the braces route, we don't need to add anything else. If we don't go the braces route, we need to add that end century thing that we would also then need to specify, but none of that exists yet. And lastly, like none of this work at all would exist without Viktor Zverevich, who is the author and main maintainer of the format library, which is awesome. He had a lot of input. There's Tim Song, who's just a genius, and Peter Dimov, who also had like a lot of really good input, and he's one of the more active Boost guys. So yeah, thank you. Yeah, any questions? Yep.
So, how does race space the person?
There's no skipping of white space. So if you want to use, so you can use, for instance, like space as a fill character, and you would do that by just putting like space caret number as your specifier. So I'm definitely not working on that. So there was this language feature that was actually approved for C++ 20 and then never happened, and then isn't happening for 23 either, which is called expansion statements. And expansion statements is basically tuple for each the language feature, and would be a lot better than like a library function tuple for each. I'm hoping just to get that we actually do like figure that out and get it into 26, because that's much better than a library facility. But the library function is pretty easy to implement because you have std apply. So you can call std apply and fold over comma, which is a very strange thing to do, but it works. So I don't know. At this point, tuple for each feels like one of these things that we should have added in C++ 17 when we added std apply. But now that like hopefully we will actually add expansion statements in 26, it doesn't make any sense to add a library facility that would be strictly worse than the language facility. Like it would compile slower, it's more awkward looking, it introduces this extra function scope. Yep. Okay, so so why did I suggest D as the specifier? Let me back up to that. Oh man. Yeah, see, this is this. Okay, so we need a way when we're parsing to know when we're up to the delimiter, and then we need a way to know when the delimiter ends. So if I'm providing like a argument for the delimiter, so if I'm using braces, so one of the issues is like, so you need to differentiate between like fill, parse, align. So you need to know when that runs out. And then you need a way to know, it's like, okay, now I'm doing delimiter. And it's just easier to stick in D there. It might not be strictly necessary because it might not be actually ambiguous with anything else, but like it would certainly help for the reader to know it's there. But once we have that, if you're trying to stick the actual delimiter into the format specifier, you don't know how long it's going to be. So it can't just be like D:, because if I want to support like a 2-character delimiter, I need to know like kind of where it ends. So I need some kind of like bounding thing, and that bounding thing can't be braces because we're already going to be using braces for. If I'm using braces for like dynamic delimiter, then I have to use something else. So that leaves brackets and parens. Unless we want to go for like the really weird delimiters, which I don't think anyone's like going full for UTF-8 just to do like very simple things. Although, you know, I'm partial to Russian quotes, which are kind of nice, but I don't think it's going to fly. Yeah.
It's an internet question. Is there anything that can make parsing easier, or do they need to do custom at all?
Yeah, so one of the things that I'm hoping we do provide at some point, although I don't know if anyone's working on this, is there's a lot of things that are common that people generally want to do. So like fill align width is like a common thing that also happens to be difficult to parse. So it would be nice if we just provided a utility that like parsed that for you and formatted things for you. I mean, the formatting part is a little bit easier, but you still have to do all this other kind of stuff with it. So if you use the format library, all of that's kind of exposed, so you can kind of find it. It's not in a particularly consumable form because like that wasn't why it was written. Like it wasn't written from the perspective of being an external API. But I feel like we should be able to come up with something. So like if you compare this, for instance, to like what Rust's format API looks like, which is very different in every way. What they have is they just have one function, and the function takes this formatter object, which already has everything parsed, and you just like use it to write things, and it just does the right thing. So it's like a lot easier to do. On the other hand, it doesn't have any custom specifiers, so you can't do any of the stuff just at all. So it's kind of a trade-off. Like it would be nice if we added more facilities to make this easier for people to write, because I mean, no one really wants to write any of this, I don't think. Yeah. Yeah. No. So if we do support for specifiers for parent tuple, which I do hope we do at some point because that would be useful, you have to provide all of them, because I don't know how we would determine it otherwise. I'm not like we would have to come up with a way of like informing the library like stop now or something. But I don't really know how we would possibly do that. I mean, maybe someone comes up with something clever, but it doesn't seem possible. There's of course a completely different way of doing this, which is like instead of trying to put it into the format string, you create an object constructed from the tuple and pass all your format specifiers directly as like a tuple of string view or something, and then handle it that way. You lose a lot actually by doing that. Like you lose any ability to check things at compile time, which is a pretty big loss. The other kind of interesting thing that you lose is like, what does that object end up looking like? Because you have to capture this tuple. You probably don't want to copy it, so you want to capture it by reference to be cheaper. But then like, what if you're using like a logging framework that is like asynchronous and like wants to send stuff over somewhere? So now like, well, this thing that you capture by reference, well, like you need a way to like copy it so that like you can actually safely do that. And then like, well, how do you make sure that you actually copy it in all the places you need to copy? So it's challenging. This is, by the way, one of the reasons that I have been pushing for more things into specifiers, is that it makes all this logging stuff a lot easier, because the thing that you're logging is the argument directly. And so like, well, if you're formatting directly, the argument's right there. There's no need to copy it. And if you do need to copy it, the thing you're copying is the thing that you need to copy, and not like some handle to it or something. And all of that becomes like much more difficult if you start wrapping this. So that like, yeah, so the seemingly easy solution to like a lot of these problems is like, well, I like just write an object that like takes that and like provide the format, the specifier for it separately, which is certainly much more readable. Like if you just like imagine what the code looks like for formatting a tuple, and like you just have a thing that takes like an initializer list of format specifiers. Well, like now it's clearly delimited. I don't have to come up with like crazy mechanisms for like how to delimit my specifiers, because like I'm just using language to do it. But it does have that like significant limitation, which kind of sucks. Yeah. Cool. Well, thanks everyone for coming. All